Welcome to Still Science Lab. Tonight, we are embarking on a journey across 1400 light-years of space to confront a mystery that has shaken the very foundations of astrophysics. Tabby's star. Is it finally proof of a Dyson swarm? For centuries, our relationship with the night sky was one of predictable elegance. We viewed the stars as constant lanterns, burning with a steady, internal fire that we believed we had mastered through the laws of thermodynamics and nuclear physics. But in the vast archives of the Kepler Space Telescope, there exists a singular anomaly that refuses to conform to any known model of stellar behavior. This star, officially catalogued as KIC 8462852 but affectionately known as Tabby's star, has presented us with a riddle so profound that it forces us to reconsider the possibility that we are not the only architects in the cosmos. Tonight, we will look deep into the shadows of this distant sun to determine if what we are seeing is a rare natural phenomenon or the first tangible evidence of a galactic-scale civilization at work. The story of Tabby's star is not just a story of data points and light curves. It is a story of how we search for the unknown. When NASA launched the Kepler Space Telescope in 2009, its mission was clear: to find Earth 2. To do this, Kepler used what is known as the transit method. It stared at a fixed patch of the sky, monitoring the brightness of over 150,000 stars simultaneously. The concept was simple. If a planet passes in front of its host star, it blocks a tiny fraction of that star's light. By measuring these rhythmic, predictable dips in brightness, astronomers can calculate a planet's size, its orbital period, and even its distance from the star. For years, Kepler was an overwhelming success, discovering thousands of exoplanets and revealing that our galaxy is teeming with worlds. But among the sea of standard light curves, one star stood out as an impossible outlier. Most planets, even giants like Jupiter, only block about 1% of their star's light. These transits are clean, symmetrical, and periodic. They happen like clockwork. However, when the data for KIC 8462852 began to stream in, it looked like nothing the scientists had ever seen. Instead of a 1% dip, the star showed massive, irregular plunges in brightness. In one instance, the light dropped by 15%. In another, it plummeted by a staggering 22%. To understand the scale of this anomaly, imagine an object so large that it blocks nearly a quarter of a sun's total output. If Jupiter were to pass in front of our sun, it would be like a tiny flea crossing a dinner plate. What was passing in front of Tabby's star was something else entirely, something gargantuan, something irregularly shaped, and something that defied the predictable orbits of gravity. What made the situation even more baffling was the timing. There was no clear pattern to these dimming events. They didn't happen every few days or months. They were chaotic. Sometimes the star would dim for a few days, and other times it would flicker for weeks. The shapes of the dips were also strange. They weren't the smooth U-shape of a round planet, but rather jagged, asymmetric slopes, as if a jagged cloud of debris or a complex structure were casting a shadow. When the Kepler algorithms first flagged this star, the automated systems were actually confused. Computers are designed to find patterns, and KIC 8462852 was a master of chaos. It was only through the intervention of human eyes, specifically the Planet Hunters Project, a group of citizen scientists, that the star was identified as something truly special. These volunteers realized that the glitches in the data weren't errors at all. They were a real, physical phenomenon occurring 1,400 light-years away. As the scientific community began to investigate, the name Tabitha Boyajian, the lead researcher at the time, became synonymous with the mystery. Her team meticulously ruled out every possible technical error. They checked the telescope's sensors, the data processing pipelines, and the possibility of nearby contaminating stars. Everything pointed to the same conclusion: the signal was real. But if it was real, what could possibly cause it? This is where the Dyson Swarm hypothesis entered the conversation. Proposed by physicist Freeman Dyson in the 1960 seconds, a Dyson swarm is a hypothetical megastructure built by an advanced civilization, specifically a Type II civilization on the Kardashev scale, to capture the total energy output of their star. Such a project would involve millions of massive solar collectors orbiting the star in a complex web. If we were to view such a construction project from a distance, we might see exactly what Kepler saw: massive, irregular, and non-periodic shadows blocking out huge chunks of light. The idea that we might have finally found evidence of alien megastructures sent shockwaves through both the scientific world and the public imagination. For decades, the search for extraterrestrial intelligence, SETI, had focused on listening for radio signals, trying to catch a hello from the void. But Tabby's star suggested a different approach: searching for technosignatures. We weren't looking for what a civilization was saying. We were looking for what they were building. The possibility was intoxicating. If a Dyson swarm was indeed under construction, it would mean that we are not alone and that our neighbors are vastly more advanced than we are, capable of engineering projects that span entire solar systems. It was a hypothesis of last resort, to be sure, but in the face of such unprecedented data, it was a hypothesis that had to be taken seriously. However, science demands extraordinary evidence for extraordinary claims. While the Dyson swarm theory provided a neat explanation for the irregular shadows, it also raised new questions. If there were massive structures around the star, they should be absorbing sunlight and re-radiating it as heat. This waste heat should be visible as an excess of infrared radiation. Yet, when astronomers pointed our most sensitive infrared telescopes at Tabby's star, they found nothing. The star was as quiet in the infrared spectrum as any other star of its type. This missing heat became the primary argument for skeptics, who began to search for natural explanations that could block light without generating heat, things like massive swarms of comets, interstellar dust clouds, or even a planet that had been consumed by the star, leaving behind a chaotic trail of debris. Tonight, we are going to navigate the narrow path between scientific skepticism and the thrill of discovery. We will analyze the comet hypothesis and why it eventually struggled to explain the sheer volume of material needed to block 22% of the light. We will look at the long-term fading of the star, a secondary mystery, where the star has been getting dimmer and dimmer for over a century, a fact discovered by digging through glass plate astronomical records from the 1890 seconds. We will explore the latest observations from the Las Cumbres Observatory, which caught the star dimming in real time and allowed us to analyze the color of the shadow, revealing whether the objects are solid like a machine or translucent like a cloud of dust. Tabby's star is a testament to the fact that the universe is still capable of surprising us. It reminds us that among the billions of stars in our galaxy, There are still anomalies that we cannot explain with our current textbooks. Whether it turns out to be a unique natural phenomenon or the first glimpse of a galactic empire, the search for the truth about KIC 8462852 has already changed astronomy forever. It has taught us how to look for the weird, how to value the observations of citizen scientists, and how to keep an open mind while maintaining the highest standards of evidence. So, join us as we peer through the telescope and ask the question that has haunted every stargazer since the dawn of time. Are we alone, or are we finally seeing the shadows of someone else's sun? To truly grasp why Tabby's star caused such a fervor in the scientific community, we must first examine the mechanics of how we see things in the dark. For the vast majority of human history, astronomy was a science of position and brightness. We looked at where stars were and how bright they appeared. With the advent of modern telescopes like Kepler, we transitioned into the era of high-precision photometry, the art of measuring the intensity of light with such accuracy that we can detect changes as small as a few parts per million. Under normal circumstances, a star is a remarkably stable engine of fusion, radiating light in a constant stream. When an object passes between that star and our telescope, it casts a shadow, a stellar eclipse that we call a transit. In a standard planetary transit, the mechanics are simple and symmetrical. Because planets are generally spherical and follow circular or slightly elliptical orbits, the light curve they produce, a graph of brightness over time, looks like a clean, well-defined U or V shape. The light drops quickly as the planet enters the star's disk, remains at a constant low during the transit, and rises just as quickly as it exits. It is a predictable geometric event that tells us the planet's size relative to its sun. However, the light curves produced by KIC 8462852 were a violent departure from this cosmic norm. When the first major dimming event, known as the D800 event, occurred, the light did not drop by a fraction of a percent. It plunged by 15%. This immediately created a mechanical crisis for astronomers. In our own solar system, if Jupiter, a planet 11 times the diameter of Earth, were to transit the Sun, it would block only 1% of the light. For an object to block 15% of the light of an F-type star like Tabby's star, it would have to be colossal, roughly half the width of the star itself. But physics dictates that an object that large would have enough mass to become a star itself, or at least a brown dwarf. If a second star were orbiting KIC 8462852, we would see its gravitational influence on the host star, causing it to wobble in space. We would also see the heat from that second star, yet the data showed no wobble and no extra heat. The object casting the shadow had the size of a giant, but seemingly no mass to match. This mechanical impossibility deepened during the even more famous D1500 event, where the brightness dropped by an unprecedented 22% beyond the sheer depth of the dip. The shape of the shadow was nonsensical. Planetary transits are symmetrical because spheres are symmetrical, but the shadows cast on Tabby's star were jagged and asymmetric. The light would often fade slowly over several days, then plummet suddenly, and then recover in a series of stuttering increases. This implies that the object casting the shadow was not a solid, round sphere. Instead, the mechanics suggest an object with a complex, irregular geometry, something with jagged edges, varying density, or perhaps a massive, trailing cloud of debris. Imagine the difference between the shadow of a marble rolling across a flashlight and the shadow of a torn, fluttering piece of lace. The marble produces a clean, dark circle. The lace produces a flickering, chaotic mess of light and dark. Tabby's star was being eclipsed by the cosmic equivalent of torn lace. The duration of these shadows also challenged our understanding of orbital mechanics. A planet orbiting a star like KIC 8462852 at a distance where liquid water could exist would typically complete its transit in a matter of hours. The dimming events on Tabby's star, however, lasted for days and sometimes weeks. For an object to take that long to cross the face of the star, it must be moving very slowly, which suggests it is orbiting at a massive distance, far out in the cold reaches of the stellar system. But the further an object is from its star, the less light it should block unless it is truly, incomprehensibly massive. To block 22% of the light from such a great distance, the occulter, the thing blocking the light, would need to be millions of miles wide. There is no single natural object, no planet or moon, that can occupy that much space without the gravity to hold itself together into a sphere. This brings us to the most unsettling mechanical detail, the lack of periodicity. In the clockwork universe of Isaac Newton, gravity ensures that what goes around comes around. If a planet transits a star once, it will do it again after one full orbit. This predictability is how we confirm exoplanet discoveries. We wait for the second, third, and fourth transit to prove the object is in a stable orbit. With Tabby's star, the clock was broken. The massive D800 and D1500 events did not repeat during the 4 years that Kepler watched the star. There were dozens of smaller dips, some only lasting a few hours and others lasting days, but they appeared at random. It was as if a swarm of objects of varying sizes and shapes were buzzing around the star in a chaotic, non-uniform cloud. Mechanics suggest that for such a cloud to exist without collapsing into a single disk or being ejected from the system, it must have been created very recently, perhaps by a collision of two planets or the breakup of a massive moon. But the odds of catching such a rare, short-lived event in the vastness of time are incredibly low. Furthermore, we must consider the translucency of the shadow. When we analyze the light during a transit, we can look at different wavelengths or colors of light. If a solid, opaque object like a planet or a metal structure blocks the light, it should block all colors equally. This is called chromatic or gray dimming. However, if the shadow is cast by dust or gas, it will block blue light more effectively than red light, much like how a sunset looks red because the atmosphere scatters the blue light away. Early observations of Tabby's star's smaller dips suggested that some of the dimming was color-dependent, hinting at dust. But the massive 22% dips were much closer to being gray, suggesting that whatever was blocking that much light was either very thick dust or a collection of solid, opaque objects. This mechanical duality, is it a cloud or is it a machine, is the heart of the debate. The sheer physical scale of the occulter required to produce the D1500 event is so large that it pushes the boundaries of material science. If it were a natural cloud of dust, it would need to be hundreds of times the mass of the asteroid belt in our own solar system, all concentrated into a single, temporary swarm. If it were a Dyson swarm, it would represent a collection of millions of individual satellites, each the size of a city, working in concert. The mechanics of the shadow tell us that we are looking at something that is not a planet, not a companion star, and not a standard disk of debris. We are looking at an anomaly that breaks the transit method of discovery. It is a stellar shadow that shouldn't exist, cast by an object that defies the standard geometry of the heavens. As we move forward, we must ask, if the mechanics of the shadow don't fit the profile of a planet, whose hand or what force of nature is casting it? In the modern era of big data, we often operate under the comforting assumption that our algorithms are the ultimate guardians of truth. We build sophisticated machines to sift through mountains of information, trusting them to find the patterns that human minds are too slow or too biased to see. When the Kepler Space Telescope was launched, it was accompanied by some of the most advanced automated detection pipelines ever conceived. These programs were designed to scan the light of over 150,000 stars, looking for the telltale, rhythmic signatures of orbiting planets. They were incredibly efficient at finding what they were programmed to find: the smooth, repeating U-shapes of planetary transits. However, the story of Tabby's star reveals a fundamental limitation of artificial intelligence. A machine can only find what it has been taught to recognize. If an anomaly falls outside the parameters of the expected, the algorithm often classifies it as noise or error and discards it. The discovery of KIC 8462852 did not happen because a computer was smart, but because humans were curious. In this third chapter, we explore the role of Tabitha Boyajian and the power of the human eye in the Planet Hunters project, illustrating why the most profound discoveries in science often happen when we stop looking at the averages and start paying attention to the outliers. The Planet Hunters project, part of the Zooniverse Citizen Science Portal, was born from a simple but radical premise: that the human brain remains the most sophisticated pattern recognition engine in the known universe. While a computer is excellent at high-speed calculations, it lacks the context and the intuition to handle data that looks messy or unique. The architects of Planet Hunters, including researchers from Yale University, realized that the Kepler data was so vast that professional astronomers would never have the time to look at every single light curve by hand. By crowdsourcing the task to the public, they gave hundreds of thousands of volunteers the chance to play detective. These citizen scientists were presented with snippets of light curves and asked to mark anything that looked like a transit. Most of what they saw was routine, but they were also given a talk forum where they could flag anything that looked weird. It was here, in the digital margins of the Kepler mission, that the mystery of Tabby's star first began to simmer. As early as 2011, volunteers like Darryl LaCourse and others began to notice something deeply disturbing about a specific star in the Cygnus constellation. While the automated software had ignored KIC 8462852 because its dimming events didn't fit the mathematical profile of a planet, the human volunteers couldn't look away. They saw the massive 22% drops in light and the jagged, asymmetric shapes that we discussed previously. They began tagging the star with words like bizarre, interesting, and giant. They weren't just checking boxes, they were discussing the data, comparing notes, and realizing that they were looking at something that broke the rules. This was the first triumph of the human eye, the ability to recognize that broken data might actually be a new phenomenon. The volunteers were essentially acting as a filter for the exceptional, catching the signals that the nearsighted AI had deemed irrelevant. Enter Dr. Tabitha Boyajian, a postdoctoral fellow at Yale who took these citizen science flags seriously. While many professional astronomers might have dismissed the erratic light curves as instrumental glitches after all, a 20% dip is usually a sign of a camera malfunction. Boyajian and her team decided to investigate the weirdness at its source. She didn't just look at the summaries, she dove into the raw data, looking at the individual pixels captured by Kepler. She worked closely with the citizen scientists, validating their observations and realizing that the anomaly was consistent across different quarters of the mission. This collaboration between professional academia and the passionate public represents a new era of democratized science. Boyajian became the bridge between the raw curiosity of the volunteers and the rigorous verification required by the scientific community. In 2015, Boyajian published the now famous paper titled "Where's the Flux?", a title that deliberately played on the acronym "What the fuck" to reflect the genuine bewilderment of the team. The paper meticulously documented the erratic dimming of KIC 8462852, and, perhaps more importantly, it admitted that the researchers were at a loss for a natural explanation. By naming the star Tabby's star in common parlance, the public and the media cemented the connection between the human observer and the cosmic mystery. Boyajian's leadership was characterized by a rare intellectual honesty. She didn't try to force the data into a conventional box. Instead, she laid out the facts. The star was stable, the data was clean, but the behavior was impossible by our current understanding of stellar systems. The power of the human eye, in this context, is not just about optical vision. It is about the ability to perceive meaningful chaos. A computer sees a drop in light as a negative number in a spreadsheet. A human sees it as a shadow and immediately begins to ask what could be casting it. The citizen scientists of Planet Hunters were able to distinguish between instrumental noise, which tends to look like random static, and physical signals, which, however strange, possess a certain internal logic. They recognized that the dips in Tabby's star had a specific texture. The leading edge of the shadows was often different from the trailing edge, suggesting a physical orientation in space. This kind of qualitative analysis is where the human mind still reigns supreme. We are evolved to spot the predator hiding in the dappled light of a forest. We are naturally tuned to find the signal in the noise. Boyajian's role also highlighted the importance of outlier advocacy in science. In a field that is increasingly driven by large-scale surveys and statistical significance, there is a risk of ignoring the black swans, the rare events that don't fit the curve. Without Boyajian's willingness to champion this single, strange star, it likely would have remained a forgotten footnote in a database. Her work showed that a single anomaly can be more valuable than 1,000 normal data points because it marks the boundary of our knowledge. If we only study what we already understand, we are just confirming our biases. To grow, science needs the "what the fuck" moments that force us to build new models and ask bigger questions. The discovery of Tabby's star also forced a reckoning with how we train our future AI. If our current algorithms missed the most interesting star in the Kepler database, what else have we missed? Astronomers are now using the data from Tabby's star to train anomaly detection neural networks, teaching machines to look for the irregular, the asymmetric, and the non-periodic. We are trying to teach our machines to be a little more like Tabitha Boyajian and her team of citizen scientists. Yet, there remains a sense that there will always be a need for the human element. There is a specific kind of wonder that an algorithm cannot feel, a gut feeling, that tells a researcher that a glitch is actually a discovery. As we move from the story of the people who found the star to the theories that attempt to explain it, we must remember that the alien megastructure hypothesis only became popular because every natural explanation felt just as weird. It was the human imagination, sparked by the human eye, that first dared to ask, if nature didn't build this, who did? Tabitha Boyajian didn't start her career looking for Dyson swarms. She started it looking for the truth in the data. And the truth she found was that the universe is far more imaginative than our software ever suspected. In the next chapter, we will look at the theory that turned Tabby's star into a global phenomenon, the Dyson Swarm Concept. We will explore the vision of Freeman Dyson and why the engineering of a godlike civilization became a serious topic of debate in the halls of Yale and Penn State. We will ask, if we were to build a structure to capture the power of the sun, would it look exactly like the chaos we see 1400 light-years away? In the early 1960 seconds, a theoretical physicist named Freeman Dyson published a brief but revolutionary paper that would forever change how we think about the technological limits of life in the universe. Dyson was not interested in the small-scale gadgets of his era. He was thinking in terms of deep time and cosmic resources. He proposed a thought experiment based on a simple, inescapable reality. Any civilization that continues to grow technologically will eventually face an energy crisis. On Earth, we have transitioned from wood to coal, then to oil, and now toward nuclear and solar power. But even if we perfectly harness every gust of wind and every ray of sunlight that hits our planet, we are still only capturing a billionth of the energy our sun radiates into the void. To a truly advanced civilization, what we call a Type 2 civilization on the Kardashev scale, allowing all that energy to escape into deep space, would be seen as a colossal waste. Dyson suggested that such a civilization would eventually choose to dismantle their own unpopulated planets or asteroids to create a vast network of solar collectors that would orbit their star, capturing its total energy output. This concept, which we now call a Dyson swarm, is the theoretical backbone of the mystery surrounding Tabby's star. The Kardashev scale, developed by Soviet astronomer Nikolai Kardashev, provides the framework for this vision. A Type 1 civilization is capable of using all the energy available on its home planet. Humans are currently estimated to be around a 0.7 on this scale. A Type 2 civilization, however, has graduated to the stellar level, harnessing the entire power of its home star, which is roughly septillions of watts of energy. To achieve this, they wouldn't build a solid, rigid shell, a Dyson sphere, because the material strength required to prevent such a structure from shattering under gravity and centripetal force is physically impossible. Instead, Dyson envisioned a swarm of millions or even billions of independent satellites, each acting as a massive solar sail or collector. These satellites would be arranged in a complex, overlapping web of orbits. From a distance, this swarm would block out parts of the star's light, and because the collectors would be of various sizes, shapes, and distances from the sun, the resulting shadows would be chaotic and irregular. This is precisely why the data from Tabby's star caused such a sensation. The jagged, non-periodic dimming events captured by Kepler are a near-perfect match for what a Dyson swarm under construction or in a state of decay might look like. When Jason Wright, an astronomer from Penn State University, first saw the light curves of KIC 8462852, he realized that the Dyson swarm was no longer just a thought experiment. It had become a viable, albeit extraordinary, hypothesis. The beauty of the Dyson swarm theory is that it explains the two most confusing aspects of the star: the depth of the dimming and its irregularity. A natural planet is limited by its size, but an artificial swarm is limited only by the amount of material available in the solar system. If a civilization were building panels the size of continents or even whole moons, they could easily block 22% of the star's light. Furthermore, because these structures would be powered by light and gravity, they wouldn't necessarily need to be in the same orbital plane. They could be buzzing around the star at all angles, creating a three-dimensional cloud of machinery that produces a flickering effect as the panels overlap and move. To an observer 1,400 light-years away, it would look like the star was suffering from a cosmic mechanical failure. However, the Dyson swarm theory is bound by the relentless laws of thermodynamics. According to the second law of thermodynamics, no machine is perfectly efficient. When a solar collector absorbs light from a star to turn it into work or electricity, it must also shed waste heat. In the vacuum of space, this heat can only be released as infrared radiation. Therefore, any star surrounded by a Dyson swarm should be a glowing beacon in the infrared spectrum. This was Freeman Dyson's original point. He wasn't telling us to look for radio signals, he was telling us to look for warm stars. If Tabby's star were hosting a Dyson swarm, we would expect to see a massive infrared excess, a signature of heat that doesn't match the temperature of the star itself. This is the smoking gun that astronomers have been hunting for since 2015. Yet, as we pointed out earlier, the initial searches with the Spitzer and WISE space telescopes found no such heat. The star appeared completely normal in the infrared, a discrepancy that has led many to doubt the alien megastructure theory. But proponents of the Dyson swarm theory haven't given up, and they offer several fascinating counter-arguments. One possibility is that the civilization is not just collecting the energy, but using it in a way that directs the waste heat away from Earth. If the collectors are tilted, or if the energy is being beamed to another location via narrow-frequency lasers, we might not see the expected glow. Another, more ominous possibility is that we are looking at a dead Dyson swarm, the ruins of a civilization that perished long ago. If the swarm has been abandoned, the collectors might have drifted, collided, and broken apart into smaller fragments. Over time, these fragments would cool down, and their heat signature would become much harder to detect, eventually blending into the background noise of the galaxy. In this scenario, we aren't looking at a thriving empire. We are looking at the ghostly shadows of a tomb orbiting a distant sun. The Dyson Swarm Concept also forces us to rethink the timeline of life. Our own civilization has only had electricity for about a century and a half. If a civilization were even 10,000 years older than us, a mere blink in cosmic time, their engineering capabilities would be as magic to us as a smartphone would be to a hunter-gatherer from the Stone Age. Building a swarm would require stellar lifting, the process of mining the star itself for raw materials, or the complete deconstruction of an entire planetary system. While this sounds like science fiction, it is a logical progression of the energy needs of any expanding intelligence. Tabby's star is the first time in history that we have found a physical object that actually demands we take these wild theories seriously. Even if it eventually turns out to be dust or comets, the star has served as a proof of concept for the search for technosignatures. As we weigh the probability of a Dyson swarm against natural explanations, we are forced to ask, is it more likely that we've discovered a rare, unprecedented natural event, or that we've finally seen the footprint of someone else? The absence of heat is a major hurdle, but it isn't a total disqualifier. In the next chapter, we will shift our focus back to the natural world to see if nature can be just as weird as an alien machine. We will explore the comet hypothesis, the idea that a massive family of giant fragmenting comets is responsible for the chaos. We will see why this was once the leading theory, and why, as we looked closer, the comet explanation started to feel just as impossible as the aliens themselves. We are caught between two worlds of thought, and the only way out is to look closer at the light. In the immediate aftermath of the Dyson Swarm hypothesis going viral, the scientific community did what it does best. It sought a more mundane explanation. In the pursuit of cosmic truth, researchers often rely on a principle known as Occam's razor, which suggests that the simplest explanation, the one requiring the fewest new assumptions, is usually the most likely to be correct. While the idea of an alien megastructure is perhaps the most exciting possibility in the history of science, it requires us to assume the existence of a highly advanced civilization capable of engineering on a solar scale. Therefore, astronomers turned their attention toward the most chaotic and unpredictable natural objects found in any stellar system: comets. The comet hypothesis became the first major scientific challenger to the alien theory, proposing that the irregular, massive dimming of Tabby's star was caused not by metal and glass, but by a gargantuan family of disintegrating icy giants. To understand why comets were considered a viable culprit, we must first look at their physical anatomy. Unlike a planet, which is a solid, clean-edged sphere of rock or gas, a comet is essentially a dirty snowball made of ices, frozen gases, and embedded dust. As a comet approaches the heat of its host star, these ices begin to sublimate, turning directly from solid to gas and creating a massive, glowing envelope called a coma, followed by a sprawling tail that can stretch for millions of miles. While the solid nucleus of a comet is far too small to block a significant amount of starlight, the clouds of gas and dust they release are enormous. If you were to place a single large comet in front of a star, it would act like a translucent veil rather than a solid wall. But if you have a massive cluster of giant comets, each significantly larger than any we have ever seen in our own solar system, their combined tails could create a massive, irregular screen of debris. The primary appeal of the comet hypothesis lay in its ability to explain the jagged, asymmetric shapes of the light curves recorded by the Kepler Space Telescope. As we have seen, a planet's shadow is symmetrical because the object is round and solid. A comet's tail, however, is a trailing, tapering structure of varying density. If such a tail were to sweep across the face of Tabby's star, it would create a slow, gradual dimming as the thin outer edge of the tail entered our line of sight, followed by a sharp, chaotic plunge in light as the denser coma and nucleus passed through. This seemed to match the stuttering light curves of KIC 8462852 perfectly. Furthermore, comets are notorious for fragmenting. As they are baked by the star's heat and pulled by its gravity, they break apart into smaller pieces, each creating its own mini-tail. A swarm of these fragments would look like a chaotic mess of shadows, which is exactly what the citizen scientists of Planet Hunters had initially flagged. This theory also provided a clever, natural solution to the missing heat problem that had plagued the Dyson Swarm theory. As we have discussed, any solid, artificial structure absorbing starlight should glow with infrared heat. But comets, being made of ice and dust on highly elliptical orbits, would only be close to the star and therefore hot enough to glow for a very brief period. For the vast majority of their orbit, they would be far away in the cold, dark reaches of the outer stellar system. By the time we pointed our infrared telescopes at Tabby's star, the swarm could have moved back into the cold zone, making their heat signature nearly impossible to detect. It was a natural way to explain why the star appeared to be blocked by something cold rather than a functioning machine. However, as astronomers began to run the mathematical models, the comet hypothesis started to show its own structural weaknesses. The primary issue was one of sheer scale. To block 22% of an F-type star's light, you don't just need a few big comets, you need a veritable army of giants. Some calculations suggested that it would take a family of hundreds of thousands of comets, each dozens of miles wide, passing in front of the star simultaneously to achieve that level of dimming. While it is possible for a star to have an Oort cloud filled with icy bodies, the gravitational event required to send thousands of them inward toward the star at the exact same time is incredibly rare. One potential trigger for such a comet avalanche was discovered nearby. Observations revealed that Tabby's star has a companion, a small, dim red dwarf star located about 880 astronomical units away. In the slow, gravitational dance of the cosmos, it is possible that this companion star occasionally drifts close enough to nudge the outer icy bodies of the system, sending a massive wave of comets tumbling toward the inner sun. This provided a plausible mechanism for the event, but it still didn't solve the permanence problem. Comets are transient objects. They burn up, they disintegrate, and they eventually clear out of the inner system. For Kepler to have caught such a massive, once-in-a-million-year comet shower during its 4-year mission felt like an extraordinary stroke of luck, perhaps too extraordinary for some scientists to accept. Another blow to the comet theory came from the color of the dimming events. When dust blocks light, it acts like a filter. Because dust particles are typically small, they are much better at scattering blue light than red light. This is why our own sky appears blue and our sunsets are red. If the shadows on Tabby's star were being cast by clouds of cometary dust, we would expect to see chromatic. Dimming the star should appear redder as it gets dimmer. Early data from some of the smaller dips showed this reddening effect, which strongly supported the idea of dust. But the massive 22% dips were much more grey, meaning they blocked all colours of light equally. This suggested that whatever was blocking the majority of the light was either made of very thick, coarse dust or solid, opaque objects like the panels of a Dyson swarm. As the debate continued, a new piece of evidence emerged that pushed the comet hypothesis to its breaking point. Astronomers began looking at historical records of the star, dating all the way back to the late 19th century. They found that Tabby's star wasn't just flickering on a scale of days, it had been steadily losing brightness for over 100 years. This long-term fading was a bombshell for the comet theorists. A swarm of comets might explain a sudden, chaotic flicker lasting a few weeks, but it could not explain why a star would lose a significant portion of its total luminosity over a century. To achieve a 100-year fade, you would need a truly astronomical amount of dust, essentially an entire planet's worth of material ground into fine powder and constantly replenished. The comet hypothesis represented the best effort of natural science to explain the inexplicable. It showed that we don't always need to jump to aliens to find chaos in the universe. Nature is perfectly capable of producing jagged shadows and irregular rhythms through the simple collision and disintegration of icy worlds. Yet, By the end of 2017, many astronomers felt that the comet theory was becoming just as expensive as the Dyson Swarm theory. It required so many specific, unlikely conditions: the perfect number of giant comets, the perfect timing of the companion star's nudge, and the perfect size of dust particles, that it no longer felt like the simple explanation. We were left in a state of scientific limbo, where the machines didn't fit because there was no heat, and the comets didn't fit because there was too much shadow. In the study of the universe, there is a fundamental law that acts as a universal tax collector, a rule so absolute that not even the most advanced alien civilization or the most chaotic natural event can evade it. This is the second law of thermodynamics. It tells us that energy cannot be used, transformed, or even blocked without some of it being lost as heat. When a star's light hits an object, whether that object is a tiny grain of cosmic dust, a massive planet, or a solar collector the size of a continent, that object absorbs a portion of the energy. To remain in a stable state, the object must eventually release that energy back into the void. Because the object is much cooler than the star itself, it does not emit visible light. Instead, it glows in the infrared spectrum. This is why the search for the mystery of Tabby's star eventually moved away from what we could see with our eyes and toward what we could feel with our heat-sensitive instruments. In this sixth chapter, we explore the missing heat signature, perhaps the most baffling piece of evidence in this entire detective story. If 22% of a star's light is being blocked, that energy hasn't just vanished into nothingness. It has to go somewhere. The fact that we cannot find it is the loudest silence in modern astronomy. To understand the scale of this problem, we have to look at the law of conservation of energy. Tabby's star is a massive nuclear furnace, pouring out an unimaginable amount of radiation every second. When we observe a 22% drop in its brightness, it means that nearly a quarter of that furnace's output is being intercepted by something. In the case of a traditional Dyson swarm, or a thick cloud of orbiting dust, that intercepted energy should heat the material up to hundreds or even thousands of degrees. At the distances we expect these objects to be orbiting, they should be glowing like a hot coal in a dark room. Astronomers call this an infrared excess. When we look at young stars surrounded by debris disks or stars with heavy dust clouds, they appear bright in infrared images, even if they are relatively dim in visible light. The heat is the smoking gun that proves something is there. When the mystery of this star first gained global attention, NASA's Spitzer Space Telescope and the Wide Field Infrared Survey Explorer, or WISE, were immediately tasked with finding this missing heat. These instruments are the most sensitive heat vision goggles humanity has ever built, designed specifically to find the warm glow of dust and hidden celestial objects. If there were a massive alien construction project or a dense cloud of cometary fragments, these telescopes should have seen it as a clear, unmistakable infrared signal. But the results were shocking. Tabby's star showed absolutely no significant infrared excess. To the eyes of our heat-sensitive cameras, the star looked perfectly normal, as if nothing were there at all. This null result was a devastating blow to the original Dyson swarm theory and the comet hypothesis alike. It created a profound paradox. How can something be massive enough to cast a shadow that blocks nearly a quarter of a sun, yet be stealthy enough to emit almost no detectable heat? One possible explanation for this eerie silence involves the geometry and distance of the shadow. If the objects blocking the light are positioned very far away from the star, perhaps thousands of times the distance between the Earth and the Sun, they would be so cold that their infrared glow would be extremely faint. At those frozen distances, the heat they radiate might fall below the detection limits of our current telescopes. However, orbital mechanics makes this explanation difficult to swallow. For an object that far away to block 22% of the light, it would have to be physically gargantuan, far larger than any planet or even a small star. It would be a curtain of material millions of miles wide. The odds of such a massive structure existing so far out in the cold reaches of space without collapsing under its own gravity are incredibly slim. Another theory focuses on the size of the particles involved in the shadow. In the world of astrophysics, the size of a dust grain changes how it interacts with light and heat. Small, fine dust particles, about the size of smoke, are very efficient at absorbing light and re-radiating it as heat that we can easily detect. But if the material is made of much larger grains, rocks the size of pebbles, boulders, or even mountains, the ratio of their surface area to their mass changes. Large chunks of rock hold onto their heat differently and radiate it less efficiently in the specific infrared bands that our telescopes were monitoring. This led to the broken planet hypothesis. Perhaps we are not looking at fine dust, but rather the jagged, massive remains of a planet that was recently destroyed. If the debris is composed of massive boulders rather than clouds of smoke, it might block the light while remaining relatively cool and invisible to our infrared sensors. However, we must also consider the most provocative explanation, the possibility of advanced engineering. If a Dyson swarm is being built by a civilization that has mastered the laws of physics far beyond our current understanding, perhaps they aren't wasting any energy at all. Some theorists have proposed that an advanced civilization might use active cooling systems or directional radiators to beam their waste heat away from the line of sight of potential observers like us. While this sounds like the plot of a science fiction novel, it is a logical engineering goal for a civilization that wants to operate with maximum efficiency or perhaps remain undetected in a crowded galaxy. If the collectors of a Dyson swarm were designed to beam energy via lasers to a distant colony or a central power hub, the heat we expect to see might simply be missing because it is being channeled elsewhere rather than being radiated in all directions. There is also a natural theory that bypasses the need for an external shadow altogether, known as the internal energy storage theory. What if the light isn't being blocked by something outside the star, but is instead being swallowed by the star itself? Some astronomers have proposed that Taby's star recently consumed a planet. When a star swallows a large gas giant planet, the gravitational energy and the foreign material can cause the star's outer layers to bloat and then cool down. This would lead to a temporary drop in the star's total luminosity. In this scenario, the missing light isn't blocked by a shadow. The star is simply shining less brightly as it struggles to digest a massive celestial meal. This would explain the lack of infrared excess because there is no external dust cloud to glow. The energy is trapped within the star's own turbulent plasma, waiting to be released over thousands of years. Yet, even the planet-eating star theory struggles to explain the jagged, short-term flickers that happen over just a few days. Internal changes in a star's structure usually happen over much longer timescales than what Kepler observed. We are left in a situation where every piece of evidence seems to contradict another. The light curves tell us there is a massive, irregular shadow. The infrared data tells us there is nothing there but empty space. The missing heat signature has become the ultimate filter through which all new theories must pass. It has forced us to look for cold solutions, involving strange interstellar clouds located halfway between us and the star, or perhaps even non-thermal physics that we haven't yet considered. As we struggle to reconcile the cold data with the dark shadows, another layer of the mystery has emerged from the forgotten archives of history. It turns out that Tabby's star hasn't just been flickering during the few years that Kepler was watching. It has been fading for over a century. This long-term trend adds a terrifying new dimension to the heat problem. If the star has been getting dimmer over decades, the amount of missing energy is even larger than we previously calculated. To understand the full scope of this mystery, we must travel back in time to the late 19th century to examine what is known as the Centennial Mystery. We will see how old glass photographic plates provided a clue that changed the entire timeline of this cosmic detective story and forced us to ask if the star is slowly dying or if a grand construction project is simply nearing completion. As if the sudden, jagged plunges of light weren't enough to baffle the world's leading astronomers, a second, even more disturbing dimension of the mystery began to emerge shortly after Tabby's star went viral. While the Kepler data provided a high-resolution window into 4 years of the star's life, it left a massive question unanswered. Was this erratic behavior a temporary storm in an otherwise normal life, or was it part of a much longer, more profound transformation? To find the answer, astronomers had to look back in time, far beyond the era of digital sensors and space telescopes. They turned to the astronomical memory of humanity, a treasure trove of hundreds of thousands of glass photographic plates stored in the basement of the Harvard College Observatory. In this 7th chapter, we explore the Centennial Mystery, where the discovery of a century-long fading trend pushed the enigma of KIC 8462-852 from a mere curiosity into the realm of the truly impossible. If the star is not just flickering but slowly disappearing, we are forced to ask if we are witnessing the gradual consumption of a sun's light by something of immense proportions. The investigation began with Bradley Schaefer, an astronomer at Louisiana State University, who realized that KIC 8462-852 happened to be in a region of the sky that had been photographed regularly since the late 1800s. Before the invention of modern electronics, astronomers captured the heavens on glass plates coated with light-sensitive chemicals. The Harvard collection, spanning from roughly 1,890 to 1,989, represents a continuous record of the night sky for over a century. Schaefer spent weeks meticulously analyzing these plates through a project called DASH, Digital Access to a Sky Century at Harvard. By comparing the brightness of Tabby's star to check stars of similar magnitude on the same plates, he looked for long-term changes that would be invisible to a short-term mission like Kepler. His findings were staggering. Between 1,890 and 1,989, Tabby's star appeared to have faded by about 14 to 15%. For a stable, middle-aged F-type star, such a decline is physically nonsensical. Under our current understanding of stellar evolution, stars like this should remain at a constant brightness for billions of years, with changes only occurring on timescales of millions of years as they exhaust their nuclear fuel. A 15% drop in a single century is like watching a human being age 50 years in the span of a single afternoon. If Schaefer's data was correct, It meant that the short-term dips caught by Kepler were just the tip of a much larger iceberg. The star wasn't just being eclipsed by passing objects. It was being steadily obscured, or its total energy output was being suppressed by something that was growing in density or coverage over the decades. However, the scientific community did not accept this centennial fade without a fight. The use of century-old glass plates is fraught with difficulty. Different telescopes were used over the years. The chemical composition of the plates changed, and even the way they were stored could affect the image quality. Critics, including Michael Hipke and a team of researchers, argued that the apparent fading was an instrumental artifact, a result of inconsistencies in the historical data rather than a physical change in the star itself. They pointed out that other stars on the Harvard plates sometimes showed similar fading due to changes in the calibration of the equipment. For a moment, it seemed like the long-term mystery might be debunked, leaving us with only the 4 years of Kepler's strange data to explain, but the mystery refused to die. In 2016, astronomers Ben Montet and Joshua Simon conducted a new, incredibly rigorous analysis of the original Kepler data. While Kepler was primarily designed to look at short-term changes, it also took full-frame images once a month. Montet and Simon analyzed these images with extreme care, correcting for every known sensor drift and instrumental bias. Their results provided a stunning confirmation of Schaeffer's historical claims. They found that during the first 1,000 days of the Kepler mission, the star faded steadily by about 0.3% per year. Then, in a dramatic shift, the star's brightness dropped by an additional 2% in just 200 days before returning to a slower fade. This meant the star was doing two things at once. It was suffering from sudden, massive dips in light, and it was also undergoing a continuous, long-term decline in its total luminosity. This dual behavior of fading and flickering made natural explanations like the comet hypothesis even more difficult to maintain. To explain a 15% fade over a century using comets, you would need an almost infinite supply of icy bodies, essentially an entire planetary system's worth of material constantly being ground into fine dust and perfectly positioned to block our view for 100 years straight. The mass of dust required would be so immense that it should have been easily detected by our infrared telescopes as a massive, glowing heat signature. Yet, as we saw in the previous chapter, the infrared remains silent. We were left with a star that is disappearing before our eyes, but leaving no thermal footprint behind. From the perspective of the Dyson Swarm theory, however, the centennial fade is not a bug. It is a feature. If we are watching an advanced civilization build a megastructure around their star, we wouldn't expect it to appear overnight. A project of that scale, dismantling planets and repositioning millions of solar collectors, would likely take decades or centuries to complete. A slow, steady fade over 100 years could represent the ongoing progress of the construction project, as more and more collectors are moved into orbit, gradually intercepting more of the star's light. The sudden flickers seen by Kepler could be the shadows of particularly large clusters of collectors, or perhaps the chaotic debris produced during the mining of a moon. In this view, Tabby's star isn't an anomaly of nature. It is a time-lapse video of a civilization reaching for Type 2 status on the Kardashev scale. The long-term fade also forced scientists to consider even more exotic natural possibilities. One theory suggested that the star might have recently swallowed a planet, an event that would release a massive burst of energy, making the star appear unnaturally bright for a short period before it gradually settled back to its original state. In this scenario, we aren't seeing the star fade. We are seeing it return to normal after a gorging event. However, the math for this doesn't quite add up either. The energy released by swallowing a planet should produce a very specific cooling curve that doesn't match the jagged, irregular behavior we see in the short-term dips. It seems that every time we find a potential natural answer, the star does something else to break the model. The centennial mystery transformed Tabby's star from a temporary curiosity into a fundamental challenge to astrophysics. It proved that whatever is happening at KIC 8462852 is not a passing phase. It is a sustained, large-scale process that has been occurring for at least as long as humans have had the technology to look at the stars. It has turned the star into a living laboratory where we can test our theories about gravity, dust, and the limits of technology. Astronomers are now scouring other archival databases, looking for similar stars that might have been ignored in the past. We are beginning to realize that our snapshot view of the universe, where we only look at things for a few years at a time, might be blinding us to processes that occur over centuries. As we stand at this crossroads of history and modern data, we must prepare ourselves for the possibility that there is no single smoking gun that will solve the mystery. We are looking at a puzzle where the pieces come from different centuries and different types of technology. The fading star of the 1,890 seconds and the flickering star of the 2,010 seconds are one and the same, and any true solution must explain both. In the next chapter, we will shift our focus to the debris itself. We will explore the dust and shattered worlds theory, looking at whether a catastrophic collision between planets could provide enough material to explain both the fade and the flicker, and why the color of the shadows might be our best clue yet to what this material is actually made of. If we are to move away from the intoxicating allure of alien engineering, we must confront a much more violent and chaotic possibility that we are witnessing the aftermath of a planetary-scale catastrophe. In the silent, vacuum-sealed theater of deep space, things occasionally go wrong. Gravity, usually the architect of order, can sometimes act as an agent of destruction. The theory of shattered worlds suggests that the erratic behavior of Tabby's star is not the result of a functioning machine, but the debris left behind by a cosmic traffic accident of unimaginable proportions. This chapter delves into the physics of dust, the mechanics of planetary collisions, and the critical discovery made in 2017 that fundamentally changed our understanding of what is actually casting these shadows. We must ask ourselves if we are looking at the tomb of a world rather than the construction site of an empire, and whether the color of a shadow can reveal the true nature of the material blocking our view. To understand the shattered world hypothesis, we must first consider the fragility of a planetary system. While our own solar system feels like a permanent, stable clockwork, it is the result of billions of years of survival of the fittest. In younger or more unstable systems, planets can be nudged out of their circular orbits by the gravity of a passing star or a massive companion. When this happens, orbits become eccentric and begin to cross one another. The result is a high-speed collision between two planets or a planet and its moon. The kinetic energy involved in such an event is enough to vaporize trillions of tons of rock, creating a massive, expanding cloud of superheated gas and jagged fragments. Over time, the gas cools and condenses into fine dust, while the larger chunks, the planetesimals, remain as a chaotic swarm of space rocks. If such a collision occurred recently around Tabby's star, It would create a massive, irregular ring of debris that would intermittently block our view as it orbits the star. The beauty of this theory is that it addresses the irregularity that so baffled the Kepler scientists. A debris field resulting from a collision would not be a uniform ring like those around Saturn. Instead, it would be a clumpy mess of varying densities. There would be thick knots of dust, followed by stretches of relatively clear space, and within these clouds, large, jagged fragments would cast the sharp, deep shadows we observed. This would perfectly explain why the star dims by 15% one year and 22% several years later, with no predictable pattern in between. Furthermore, a planetary collision would naturally produce a wide range of particle sizes, from microscopic soot to boulders the size of cities. This mixture of materials could explain the confusing data regarding the translucency of the shadows, where some events seem to block all light like a solid object, while others act more like a filter. The breakthrough in testing this dust theory came in May 2017, when Tabby's star began to dim again for the first time since the Kepler mission ended. Because the astronomical community was now prepared, a global network of telescopes, including the Las Cumbres Observatory, was able to watch the event in real time across multiple wavelengths of light. This was a critical moment because it allowed scientists to perform a color analysis of the shadow. If the object blocking the light were a solid, opaque structure like a Dyson Swarm panel, it would block all colors of light equally. However, if the blockage was composed of dust, it would exhibit a phenomenon known as extinction or scattering. Smaller particles are much more effective at blocking shorter wavelengths of light, such as blue, while allowing longer wavelengths, such as red, to pass through. The data from the 2017 event, nicknamed Elsie, provided a definitive answer. The star became significantly redder as it dimmed. This was the smoking gun for dust. It proved that whatever was passing in front of the star was not a solid, metallic wall, but was at least partially translucent. The shadows were being cast by a screen of material that allowed some light to filter through. Much like smoke from a forest fire makes the sun look redder on Earth. This discovery was a significant blow to the solid megastructure hypothesis, leading many researchers to conclude that the mystery was finally solved. It was simply a very large, very strange cloud of dust. But, as is always the case with this star, solving one part of the puzzle only revealed deeper contradictions. If the dust is the result of a shattered planet, we are still left with the problem of the missing heat signature. As we explored in previous chapters, the second law of thermodynamics is unforgiving. Dust absorbs starlight and must re-radiate it as infrared heat. While a planetary collision creates a lot of dust, it also creates a lot of surface area for that dust to catch the sun. The fact that our infrared telescopes see almost no excess heat means that if this is dust, it must be cold, dust material that is very far from the star, or material that is distributed in a very specific, thin geometry. This has led some to propose the exomoon or ablating planet theory. In this scenario, a large planet is orbiting so close to the star that its outer layers are being literally boiled away by the stellar wind. This would create a trailing comet-like tail of dust and gas that stays relatively close to the planet's orbit. If the planet is on a highly elliptical orbit, it might only outgas when it is near the star, creating temporary clouds that then drift and cool. Another fascinating variation is the ringed planet hypothesis. What if Tabby's star has a giant planet with a ring system hundreds of times larger than Saturn's? If those rings were tilted relative to our line of sight and contained large, irregular gaps or clumps of moons, they could produce complex light curves. However, for a ring system to block 22% of the star's light, the rings would have to be nearly as large as the orbit of the Earth. Maintaining the stability of such a massive structure against the radiation pressure of the star would be a Herculean task for nature. It brings us back to the same problem. Every natural explanation for Tabby's star requires a 1 in a billion event. We are either witnessing the most spectacular planetary collision in the history of astronomy, or we are seeing a natural phenomenon that we didn't even know was possible. Even with the 2017 evidence pointing toward dust, the Dyson Swarm proponents remain undeterred. They argue that a dusty signature doesn't necessarily rule out aliens. If a civilization were building a megastructure, the process of mining asteroids and planets would inherently create massive amounts of industrial dust and debris. We might not be looking at the finished solar panels, but at the construction dust and waste material produced by a massive engineering project. Or, perhaps more hauntingly, the dust could be the result of a Dyson swarm that is falling apart, a necrosignature of a civilization that has long since vanished, leaving their machines to collide and grind each other into powder over thousands of years. In this view, the reddening of the star is the color of a decaying tomb. As we move forward, the debate has shifted from what is it to where is it? If the material is dust, is it located within the stellar system of Tabby's star, or could it be something much closer to home? Some researchers have suggested that the dust might be located in the interstellar medium, the space between us and the star, perhaps a strange, dark cloud drifting through the galaxy that just happens to be crossing our line of sight. This would explain the lack of infrared heat from the star itself, as the dust would be cold and isolated in the void. However, the complexity and speed of the light changes make an interstellar cloud unlikely. They usually move far too slowly to cause such rapid flickering. The mystery of the shattered worlds has taught us that the color of a shadow is just as important as its depth. By looking at the star through different filters, we have learned that we are looking through a screen of particles, not a solid hull, but the sheer volume of that material, its lack of heat, and its century-long persistence continue to defy a simple natural label. We are left contemplating the destruction of worlds, whether by natural collision or by the deliberate deconstruction of a planetary system for its resources. As we prepare for the next phase of our investigation, we must turn our ears to the cosmos. If someone is building or destroying things on such a scale, are they also making noise? In the next chapter, we will explore technosignatures and the search for SETI, where we look at the efforts to catch a radio signal or a laser pulse from the heart of the mystery. When the shadows of Tabby's star first captured the public imagination, the scientific community realized that passive observation through light curves and infrared scans would no longer be enough. If there was even a remote possibility that KIC 8462852 was home to a Type II civilization capable of constructing a Dyson swarm, then that civilization might also be producing other technosignatures, detectable signs of technology that go beyond mere engineering. For decades, the search for extraterrestrial intelligence, or SETI, had been a field operating on the fringes of mainstream astronomy, often struggling for funding and academic respect. But the mystery of Tabby's star changed the stakes overnight. It provided a specific, high-value target for our most sensitive ears. In this 9th chapter, we explore the high-stakes hunt for radio signals, laser pulses, and the noises of an advanced society, examining why the silence we found might be just as telling as a loud hello from the void. The first major response came from the SETI Institute, which directed the Allen Telescope Array in Northern California toward the Cygnus constellation. The goal was to listen for radio emissions that could not be produced by natural processes. In radio astronomy, we look for narrowband signals, signals that occupy a very small range of frequencies. Nature is broadband. Things like pulsars, quasars, and lightning produce radio noise across a wide spectrum. Only technology, as far as we know, can concentrate energy into a single, sharp frequency. The Allen Telescope Array spent weeks scanning the frequencies between 1 and 10 gigahertz, looking for pulses that might indicate a communication beacon, or even the leakage of an alien internet or radar system. However, after hundreds of hours of listening, the researchers reported that no such signals were detected. To our radio ears, the space around Tabby's star was as quiet as a tomb. This initial silence did not deter the search. If anything, it intensified it. In 2016, the Breakthrough Listen project, a $100 million initiative funded by Yuri Milner and supported by the late Stephen Hawking, joined the fray. They utilized the Green Bank Telescope in West Virginia, the world's largest fully steerable radio telescope, to conduct the most intensive scan of a single star system in history. Breakthrough Listen brought a level of sensitivity that was orders of magnitude higher than previous efforts. They weren't just looking for intentional beacons, they were looking for low-level emissions. But even with the world's best equipment, the results remained the same: null. There were no radio waves that suggested the presence of an active, broadcasting civilization. To understand why this silence is so perplexing, we have to consider the distance. Tabby's star is 1,400 light-years away. This means that even if a civilization there were at our current level of technology, we would never be able to hear their leakage. Our own radio and television signals become indistinguishable from background noise after just a few light-years of travel. To hear someone from 1,400 light-years away, they would have to be aiming a high-powered, intentional beacon directly at Earth, or they would have to be using energy on a scale that dwarfs our entire planetary output. If the civilization is advanced enough to build a Dyson swarm, they should have the energy to make themselves heard. The fact that they haven't suggests one of three things. They aren't there, they aren't talking to us, or they are using a form of technology that we don't yet know how to detect. This led researchers to shift their focus from radio waves to light itself, through a field known as optical SETI. If a civilization wanted to communicate across the vast distances between stars, lasers would be far more efficient than radio. A laser beam can carry massive amounts of data and can stay tightly focused over trillions of miles. Programs like the Boquete Optical SETI Observatory in Panama and various teams at Harvard searched for nanosecond-scale flashes of light coming from KIC 84-62852. They looked for photonic pulses that would indicate a laser-based communication network, or perhaps the use of laser sails to propel spacecraft between planets. Just as with the radio searches, the optical telescopes found nothing but the steady, albeit flickering, light of the star. Despite these failures to find a signal, The search for technosignatures has fundamentally redefined the Dyson swarm hypothesis. Some theorists have proposed that we are looking for the wrong kind of noise. If a civilization is truly advanced, they might not use radio or lasers at all. They might use neutrinos, tiny, ghost-like particles that pass through matter almost unimpeded, or even gravitational waves to send messages. Others suggest that the noise we should be looking for is the mechanical sound of the swarm itself. A collection of millions of satellites would inevitably collide, grind against each other, and produce a specific type of shimmering in the star's light that is different from natural dust. We are currently developing the mathematical tools to distinguish this mechanical shimmer from the chaos of a natural debris disk. The silence of Tabby's star also brings us back to the Great Filter theory, the idea that there is some barrier to the long-term survival of intelligent civilizations. If we are looking at a Dyson swarm that is no longer broadcasting, are we looking at a monument left behind by a species that has gone extinct? Or perhaps we are looking at a civilization that has transcended the need for physical communication, moving into a post-biological state where they live inside their machines, consuming the star's energy in total silence. In this scenario, the Dyson swarm isn't a power plant for a city. It is the body of the civilization itself. This would explain the lack of signals. They aren't sending data, they are the data. The involvement of SETI in the Tabby star mystery also highlighted the importance of serendipitous discovery. For decades, SETI was criticized for looking for needles in haystacks without even knowing if there are any needles. But Tabby's star gave us the haystack. Even if the star turns out to be a natural phenomenon, the effort to listen to it has refined our techniques, improved our algorithms, and created a template for how to handle the next anomaly we find. We have learned how to coordinate global telescopes in real time, how to filter out human-made radio interference, and how to stay skeptical while remaining hopeful. As we move toward the final chapter of this journey, we must reconcile the great silence with the great shadow. We have a star that is fading and flickering in ways that nature struggles to explain, yet it remains as quiet as a mountain in terms of communication. This tension is where the true mystery of Tabby's star lives. It forces us to confront the limits of our own imagination and the possibility that the universe is filled with dark technologies, things that are massive and world-changing, but entirely invisible to our current ways of thinking. In the final part of our investigation, we will bring all these threads together. We will look at the legacy of KIC 8462852 and how it has changed the way we look at the night sky. Whether it is finally proof of a Dyson swarm or a spectacular new class of natural phenomenon, Tabby's star has already succeeded in doing something no other star has done. It has made us realize that the most important thing we can find in the dark is not an answer, but a better question. We will conclude by looking toward the future to the next generation of telescopes like James Webb and the Extremely Large Telescope, and ask if we are finally on the verge of solving the mystery, or if the star will remain a silent riddle for centuries to come. As we reach the conclusion of our journey across the light years to Tabby's star, we find ourselves standing at a unique threshold in the history of science. For nearly a decade, KIC 8462852 has acted as a mirror, reflecting our deepest curiosities, our technological anxieties, and our relentless drive to categorize the unknown. What began as a series of strange glitches in a NASA database evolved into a global phenomenon that forced the finest minds in astrophysics to reconsider the very nature of stellar behavior. The legacy of Tabby's star is not found in a single, tidy answer because, in truth, the mystery remains partially veiled, but in the way it has fundamentally reshaped our approach to the cosmos. It has taught us that the most significant discoveries often hide in the data that we were tempted to throw away, and that the universe is far more inventive than our most advanced algorithms ever suspected. The first and perhaps most enduring legacy of this star is the validation of human intuition in the age of artificial intelligence. In an era where we rely on machine learning to process petabytes of information, Tabby's star stands as a monument to the power of the unfiltered human eye. The Planet Hunters project proved that while a computer is excellent at finding what it has been told to look for, the human brain is uniquely equipped to find what it does not recognize. This realization has sparked a revolution in how we design future space missions. Astronomers are now creating anomaly detection pipelines that are specifically designed to ignore the average and flag the bizarre. We are no longer just looking for Earth 2. We are looking for the weird, the impossible, and the unexplainable. Tabby's star has given us the permission to be curious about the outliers, transforming the way we hunt for the secrets of the galaxy. Furthermore, Tabby's star has successfully moved the search for extraterrestrial intelligence, SETI, from the fringes of speculative science into the mainstream of academic rigor. By presenting us with a physical anomaly that could not be easily explained by natural laws, it forced scientists to treat technosignatures as a legitimate hypothesis rather than a plot point for science fiction. The Dyson Swarm theory provided a framework for what an advanced civilization might actually look like from a distance, moving the conversation away from radio hellos and toward the tangible footprints of cosmic-scale engineering. Even if the shadows of Tabby's star ultimately prove to be natural dust, the methods we developed to test the alien hypothesis using radio telescopes, optical laser detectors, and thermodynamic analysis have created a blueprint for every future search for life among the stars. We are now better prepared to recognize a true megastructure if we ever encounter one. In the realm of natural science, the star has forced a profound revaluation of stellar environments. We once thought we understood the life cycles of F-type stars and the stability of their planetary systems. Tabby's star shattered that complacency. Whether the cause is a family of hundreds of thousands of giant comets, the debris of a shattered planet, or a star that has recently gorged itself on its own worlds, the natural chaos models we've developed have pushed the boundaries of orbital mechanics. We have learned that planetary systems can be far more violent and unpredictable than our own solar system suggests. We have discovered that stars can flicker and fade on timescales that we previously thought impossible. Tabby's star has reminded us that nature is capable of creating complexity that rivals anything we could dream up in a laboratory. The technical legacy of the star is also tied to the democratization of science. The story of Tabitha Boyajian and her collaboration with citizen scientists is a template for the future of research. It showed that the wall between the professional and the amateur is becoming increasingly porous. When the 2017 dimming event occurred, it was a crowdfunding campaign that allowed for the continuous monitoring of the star. People from all over the world, from all walks of life, contributed to the search for the truth. This global participation has created a sense of shared ownership over the mysteries of the universe. We are no longer passive observers of the discoveries made by a handful of elites. We are all participants in the cosmic detective story. As we look toward the future, the hunt for the truth about KIC 8462852 is far from over. A new generation of instruments is now coming online that will provide the clarity we've been missing. The James Webb Space Telescope, JWST, with its unprecedented infrared sensitivity, is the perfect tool to finally settle the debate over the missing heat. If there is even a trace of thermal radiation from a hidden swarm or a dusty debris field, James Webb will find it. Similarly, the Vera C. Rubin Observatory, currently under construction in Chile, will conduct the most comprehensive survey of the sky in history, monitoring billions of stars for the kind of flickering behavior that made Tabby's star famous. We may soon find that Tabby's star is not a one-off miracle, but the first member of a whole new class of celestial objects, stars that are undergoing catastrophic changes or hosting massive engineering projects. Perhaps the most philosophical legacy of this star is the value of the unsolved. In a world that demands instant answers and binary truths, Tabby's star has remained a persistent maybe. It has occupied a space between the known and the unknown for over a decade, and in that space, it has fueled our imagination. It has inspired children to become astronomers, prompted philosophers to ask what it means to be a Type 2 civilization, and reminded us all that there are still things under the sun that we do not understand. There is a specific kind of beauty in a mystery that refuses to be solved easily. It keeps us humble and it keeps us looking up. As we conclude tonight's journey at Still Science Lab, we leave the star KIC 8462852 right where we found it, 1400 light-years away, flickering in the shadows of the Cygnus constellation. Whether those shadows are cast by the jagged remains of a dead world or the soaring panels of an alien empire, they serve as a reminder that we live in a universe of infinite possibilities. We have learned how to listen, how to look, and how to doubt. But most importantly, we have learned how to wonder. The legacy of Tabby's star is not a final chapter. It is a prologue to a future where we are no longer surprised by the weirdness of the heavens, but are instead ready to greet it. Thank you for joining us in the shadows. From everyone here at the lab, keep your eyes on the data, but never stop dreaming of what lies behind the light. Good night, and see you in the next video.